C-Therm's purpose is to simplify thermal conductivity testing for the materials of tomorrow. Since 2007, we have emerged as the global leader in test instrumentation. Our core strength in thermal conductivity is built on now industry standard Trident instrument and broadened through strategic partnerships with Rigaku and Metrovid, providing one of the most dynamic portfolios in thermal and mechanical analysis.
Thermal conductivity describes a material's ability to transfer heat energy through conduction. In electronics, whether you're developing a smartphone, aircraft, or electric vehicle battery pack, the thermal conductivity of the materials is a major factor in the overall thermal management of the device. In other applications, like metal hydrides that are used as hydrogen storage media in fuel cells, the thermal conductivity impacts the kinetics of hydrogen adsorption.
The most common mistake we see in industry is applying a good method of measurement on the wrong type of sample. This is what happens when you're limited to a single tool and are facing a variety of sample formats. The Trident was designed to provide researchers with multiple options on a single instrument platform, so you always have the right tool for the job. It's been a huge success. Leaders like NASA, Additives, Intel, Kimberly-Clark, Lucid Motors, and universities around the world choose C-Therm analysis tools and the support we provide.
C-Therm customers get access to the most advanced transient methods and are able to test under real-world application conditions, including humidity, temperature, or pressure. C-Therm's patented MTPS single-sided sensor is the fastest and easiest way to measure thermal conductivity. The Flex TPS is brilliant for more challenging applications and testing anisotropic and thin film samples. Our needle probe offers robustness for polymer melts. And the new THW is great for low viscosity fluids like engine coolants.
Not every client's ready to bring testing in-house, so we also offer industry-leading testing services here at Thermal Analysis Labs. C-Therm's highly skilled and experienced team provides access to the most advanced characterization tools for thermal properties and the expertise to make sense of the test results. For example, Rigaku's breakthrough sample observation capabilities allow users to video record a sample as it undergoes a heating cycle. When working with an unfamiliar material, you can see phase changes, crystallization, and other phenomena. This is vital for understanding the material and helping tell the story of how it behaves.
Metrovib's line of DMA offers the broadest frequency range and the highest force available on the market. This is just one of the reasons it is the standard in the rubber and tire industry. We work with a lot of folk developing different fillers for tires, including carbon black. And due to its sensitivity, the DMA is by far the best method to measure the glass transition point.
C-Therm aims to help accelerate material research and improve outcomes driven by better material performance data. Let us help you get the best possible data for your research, simplifying thermal conductivity.
All right. Good day, folks. Just getting things set up here for today's session. For those of you currently on the line, we will begin the formal session here in about a minute or two. A couple announcements just wanted to make before we jump into it. Today's session will be recorded and available for playback later on. You will be able to access those via the links that will be provided. Also, during today's session, if you do have any questions, we will be doing a formal Q&A at the end of the presentation today. So please feel free to make use of the chat box feature, the Q&A. If you have any questions, you can type those in, whether it's related to content presented here today, or maybe something related to what you're working on. Definitely feel free to send those our way, and we can discuss that at the end of the session. So just looking about a minute past the hour, we'll go ahead and jump into it. So hello, everyone. My name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies. I'm just going to be setting up a little bit of an introduction here today for our main speaker, my colleague, Genesis Infante, who will be coming and joining us here briefly. Today's session will be going over differential scanning calorimetry, also known as DSC, specifically looking at applications in polymers and composites. So that'll be really the main focus for today's presentation. Before we go into the main session here, just wanted to do a little bit of an introduction to really who C-Therm is and our partners, for those who may be new and unfamiliar. Really here, C-Therm Technologies, what our main focus on is thermal conductivity. This is what we live and breathe, especially focusing in on the transient class of measurement for thermal conductivity. Again, really the goal here is simplifying thermal conductivity testing for the materials of tomorrow. And we really focus and drive this through the development of these transient methods. Specifically on Trident, our main instrument platform. This is a modular system designed to accommodate various testing needs, whether it's related to the sample type, the testing conditions you are looking to replicate, or others. There's a variety of methods here that can really allow you to pick and choose the best tool for the task at hand. Now, not the main focus for today's session, of course, but if you did have any questions related to thermal conductivity as well, certainly happy to answer those. The idea behind Trident really is, it stems from this famous quote from Abraham Maslow, when all you have is a hammer, everything looks like a nail. And this can really truly be applied to any testing instrument where it might be designed to do one thing very well, maybe testing of, let's say, solids, but not so great at dealing with the liquids, just as an example. So again, the idea here with the modularity gives you more of that toolbox approach to pick the best tool for the task at hand. If you are interested in learning more about thermal conductivity, we do have a free method selection guide available for download on our website. This kind of really goes over a lot of the different transient methods that are available on Trident, as well as other methods that are in instruments out there in industry. Again, if you're new to this space, or maybe you want some review of what's going on and what options exist, definitely a good option to take a look at. It's a free resource. Definitely feel free to take a look at that if that's of interest. But we also wanted to just highlight that while we focus on thermal conductivity, we are partnered with various groups for other material properties. Specifically, today's focus will be looking at DSC. So Rigaku has an extensive thermal analysis line for DSC, STA, and TMA. We partner with them and are their distributors in North America. And again, if there was going to be any questions in today's session, we'll be really focused more so on this aspect of material characterization. But we also work with a group in France, Metrovib, for their line of DMA instrumentation. So whether you're looking at thermal conductivity, more standard thermal analysis, or mechanical analysis, we can certainly help depending on what those needs are. Lastly, I will mention we also have a full-service test lab, Thermal Analysis Labs. This is available for contract testing for all of the instrumentation that we offer, as well as other instruments and test methods available in industry. So if you'd like to learn more about any of these product lines or any of the resources that we have, maybe you want to really talk more one-on-one about exactly what you're working on, we'd be happy to schedule a technical consultation, give you a chance to really let us know what you're looking for. Maybe we can show you a demonstration of how the instruments work. Alternatively, if you're looking to, maybe, I know end of year is coming up, some folks are trying to allocate budget. If you'd like a quote to kind of get an understanding of what that would cost to bring something like this in-house, we can certainly help with that as well. So I'd like to end here just with a client testimonial. We always like to, say what our clients are saying about us, and just kind of see, this one here noting that they're using the C-Therm MTPS, that it combines speed, precision, and accuracy to provide our development, quality, and production teams trustworthy thermal conductivity measurements. It's enabled them to more rapidly customize solution for their customers, as well as provide quick and timely customer support. So this is a group, Crosslink Technologies Limited. We do have a variety of testimonials available on our page on our website. If you'd like to check out what other folks are saying about their experiences with us, please feel free to do so. But that, kind of sets up a little bit of an introduction here today. At this point, I will hand it over to my colleague, Dr. Genesis Infante, who is our laboratory services manager here at C-Therm Technologies, to really take us through to the body of today's work, focusing on DSC applications in polymer composites. All right. Thank you, Genesis.
All right, so hello everyone. Thank you, Arya, for the quick and detailed introduction right there. So as Arya said, today's webinar will be focusing on an in-depth look into the DSC applications, and specifically applications with polymers and composites. So I would like to start this session going through how the DSC works and what are our test parameters that we need to be considered in order for us to better understand and also make sure that how we're doing the DSC technique is within the proper and good experimental conditions. So starting with the definition, I would like to just define it, like what exactly is the DSC. It stands for Differential Scanning Calorimetry. And what it is exactly is that it is a quantitative measurement of a physical or chemical changes occurring in the materials in response to temperature change. So what it does is it looks into endothermic and exothermic processes and changes in the more intrinsic properties of the materials, such as heat capacity. So how it works is that it measures the difference of the heat flow required to increase the temperature of the sample and relative to a reference material in the DSC test. For DSC types, typically there are two different main types available commercially. There is the heat flux type and the power compensation type. So depending on the type of DSC, there's pros and cons in there, different instrumentations and different considerations when it comes to sensitivity and robustness against noise. So for the most part, we'll be covering the heat flux type, as it is the most common type of DSC nowadays. But it's also known to be well manufactured and very robust against thermal noise and whatnot. So on its basic principle, the way that DSC works is that the sample, which is going to be loaded into this sample test chamber right here, and what this test chamber looks like is going to be something like this, where you have two different locations where a reference material or reference pan is located, and a sample pan where it's going to be containing the sample test material is going to be located on the right side, and we're going to have like a heater block and a thermosensitive plate for detection. Specifically for this particular DSC, you'll see that there is usually kind of something that like a claw or a part of the design where it's going to have to secure the pan, so that to ensure that during the test itself, the pan that contains the sample and the reference doesn't move for one reason or another. The basic principles again for DSC is that typically we'll be looking at heat flow. As you can see here, usually in a normalized function, like in watts per gram, normalized against the mass of the sample. And you'll see it typically in the x-axis and something like as a function of temperature. This can be also easily be interchanged as a function of time, where the rate of temperature change is also added in the graph. Another important thing that we folks would be looking at when we're looking for the DSC graphs would be a directionality indicating which direction is exothermic and which direction is endothermic. So what it means exactly is that, like, for example, like something like a glass transition right here, you can see that there is a baseline shift, typical of like if there's a softening or the polymer material is undergoing some sort of a glass transition. You can see that the baseline shifts into the more endothermic direction. And something like an exothermic process can generate a graph looking like this, where you can see that there is a significant increase of the heat flow generated from the something like a chemical reaction or a crystallization event, where there is a heat released and the detector is receiving a signal where now there's an added heat flow occurring in the system. So this, because we have the exo up directionality in our graph, you can see that it is an exothermic event. And of course, the opposite of that would be something like an endothermic event, where heat is typically absorbed. This is typically associated with something like a melting event or something different. But for polymers, typically it's going to be something like a melt. In terms of analyzing exactly, like in a more quantitative sense, what we can exactly gather from the DSC curves, we can get like different information like the melting temperature and the onset and whatnot. So for example, like if you look at the glass transition right here, where you can see that there is a baseline shift. Another type of glass transition typical of DSCs or materials in polymers usually is something like a glass transition with an enthalpy relaxation. So you can see like a big dip in the energy and a baseline stabilization right here. So from all this curve, what we can get from this is like what we call the onset temperature. And if we're asking for something like, or for trying to measure something like a temperature where an event starts occurring, usually we are referring to the onset temperature, not the middle point temperature, right? As right here. Another temperature important data you can gather from here would be something like an extrapolated end temperature, where the event, what the temperature where the event is now finished occurring. It can be useful for your data when you're looking at polymer events usually. Similar with this particular curve, now we have like a different definition where we're going to start extrapolating the onsets. You can see here there's different tangent lines that we're considering. So instead of like for the middle point, for example, we're not considering the minima in this particular dip in the curve, but we're considering about a baseline to baseline difference. And of course, for the endothermic and exothermic peaks, again, onset temperature is something along the line of like a tangent line, where the peak temperature or the middle point intersects with a baseline. So that's like how we define onset temperature. So again, if you're looking for something like a melting temperature, this is where we would define it, not the peak temperature right here, but the onset temperature. And the end temperature, again, is going to be something of a useful temperature to take note of, just in case you have something like a more amorphous semi-crystalline polymers, as we would be discussing later on. Another information that we can gather is the area under these curves are typically referred to as the enthalpy energies. So this would be something like a energy of the melt. So integration under that line or that curve corresponds to the energy associated with that particular event. So the same applies with the exothermic event, so something like a crystallization or a reactive, like an oxidation event, where you're going to have the release of energy, and that energy associated with is going to be defined or characterized by the area under this curve. So another feature typically associated with DSC, and again, this is going to be typically added into the software itself, would be the derivative of the curve, the DSC curve itself. So you can see this is the original DSC curve, and you can see that the derivative of that looks like something like this. So what this derivative really describes is basically the change in the slope of the curve, so effectively describing the rate of change of the heat flux during the event, right? So for example, right here, you can see that the event is minima, and like the slope is minima at this point right here, so associated right about here, and maximum at about right here. So we can extrapolate or get the rate of reactions, for example, from those data. And another important factor that we might need to consider when we're using the DSC techniques in general is that this technique is typically calibrated against well-behaving and well-known materials. So depending on the temperature range that we're looking at, typically what we're looking at something like a cyclohexane to calibrate it at really low temperatures, and a nickel for really high temperature applications. So what we're looking for here is that when we're measuring this reference materials, you have to make sure that the DSC instrument is measuring the correct melting temperature. So in this case, the onset temperature, and the melting energy measured under the curve right here. So if in a case that there is some discrepancy and differences between the temperature and energy verification or calibrations, we might need to consider to contact someone to kind of look into your DSC instrument and to make sure that it is working properly. So a very important consideration when we're looking at the DSC is that how we're going to handle the sampling itself. So we can start with like actually choosing the type of sampling pan or crucible that we're going to use to contain our samples. And there are different types of pans available out there commercially. So typical pans could be something like an aluminum, alumina, ceramics, a platinum metal, glass, and a stainless steel, for example. So all of these factors that you have to consider is like different factors such as reactivity with your sample. So you don't want your samples to be reacting actively with the pan that you're using. So you want to make sure that the pan and the samples are inert against each other. The temperature range that you want to look into. So for example, the alumina or aluminum pan can only go up to about 500 degrees C, maybe 600, because the melting point of aluminum is about 650 or so. So for safety purposes, you probably don't want to use the aluminum pan beyond 500 degrees C. So there's going to be like softening factor. So you don't want to make sure that the crucible that you're using is within the temperature that you're looking for. And rarely, sometimes DSC studies can be involved pressures. So some pans are designed to be able to contain high pressure, such as this stainless steel pan, where there's some sort of like a lid threads, or a certain way of sealing it. Aluminum pans, usually you can also seal it to be able to handle relatively high pressure. If there's enough, if there's a significant vapor pressure going on, or if you just want to test your sample under a particular pressure itself. Another important factor to really look into is the consideration of thermal conductivity. So different materials will conduct heat differently, and as DSC goes, the DSC detects the change in the case of a thermal event. So if a thermal event occurs in the material slash crucible, that heat has to be somehow detected by the detector in the test chamber. Depending on the pan that you use, there's going to be different rates on how that heat is going to be transferred from the pan into the detector itself. So, for example, aluminum or ceramic type crucibles have a lower thermal conductivity, something like an aluminum, right? So you can see here that it's the signal is a little bit more broader, like less sharp as compared to the aluminum, because the heat is going to be conveyed across the pan in a slower manner. So if you get like the area under the curve right here, it's going to be equal to each other. It's just that the sharpness and the resolution will be a little bit different depending on what you use. Another important factor again is that to consider, it would be something like a crimping versus sealing. So different application might need certain, if you want to insulate or isolate your sample during the test itself. So let's say if you have like a evaporation or some sort of like a phase change, that you might want to make sure that there's no significant change in your sample during the test. Is that crimping is by definition used to increase the contact between the sample and the pan. But you have to make sure that you have to keep in mind that this doesn't mean that it is sealed against high pressure conditions. So if you want to make sure that your sample is actually touching the bottom of the surface, which is what you want to know or what you need in general, because you want to make sure that the contact between the sample and the pan is maximized as much as possible. But in terms of sealing it, you want to prevent dehydration or loss of mass during your reaction. So for example, right here we can see there's a benzoic acid test. So there's two tests, identical amounts, identical heating rate and whatnot. But for crimp pans or aluminum pans, it doesn't account for it's not completely sealed. So during sublimation, you can see that there is a shift on the baseline because you're losing mass as it goes, and that shift increases as in a higher temperature due to evaporation of your material. So again, you get similar data or similar intensity, but you got this error right here that needs to be accounted for, which you probably want to make sure that you're doing the best possible condition in terms of sample prep. And speaking of sample prep, sometimes if you want to if you're dealing with something like, if you want to powderize something, you want to grind it down. So for something like a polymer application, that can be an important factor, especially if you're considering recycling and, looking into what kind of polymers are available in that particular mix. And you can see here that without any type of grinding and conditioning, you can see that there is this profile for in this case it's the crystalline caffeine. But after grinding that crystal and retesting it, you can see that there is a shift right here where now it's significantly in a lower temperature. However, the melting profile is still pretty much identical to each other. So it's just something to keep in mind, that sample prep can somehow introduce bias into your measurements. And another important factor is sampling size. So here is an example where it's the same DSC conditions, heating rate, the same temperature range, but with different amounts. And you can see that the intensity and the resolution is going to be different with higher amounts, meaning a slight shift into a higher temperature in terms of the onset temperature and the peak temperature and the end temperature. So, however, because the energy is normalized against the mass of your sample, you can see that the energy under when you integrate the area under the curve, you can see that it's practically identical. So, something to keep in mind is that the different size amount in terms of sampling can affect your sensitivity and resolution. So if you're looking for increased sensitivity, you might want to consider having a large sample amount. But if you want to make sure that if you have multiple peaks that are involved, you might want to increase the resolution. So for example, melting of a deuteriacontane, which is typically used for lubrications, you can see that there is two distinct peaks right here. So from blue to purple is the increasing amount of sample used when testing. So, it makes sense that you have really small signals when you're using really small amounts, but you can see here that the peaks are really distinct from one another. So again, you can see it from here. And as you increase the amount of the sample, you can see that the peaks starts overlapping one another. So what it does is that you get information such as, oh, we get two peaks right here for sure. But if you want to have more refined, let's say the associated energy under this peak, you can see that the energy is about 90.7 and 171.8. And then when you have in higher amounts, that value changes a little bit, right? So you want to make sure you want to balance out resolution versus sensitivity when dealing with DSC. Heating rate is also another important factor. So again, the same sample, but different heating rate. So increasing resolution typically means, you have a sharper multiple peaks, would be something like in a slower heating rate. So 0.5 versus 10 degrees Celsius per minute right here. So again, you have the separation of the peak versus actually getting signals from different peak. So all of this consideration is very important, especially if we're going to be, looking at applications for polymers and composites, because different polymers would behave differently depending on what you're looking for specifically, right? So DSC techniques in terms of using with polymers, you can get very different results depending on your intent, right? So you can measure heat capacity if you want to, kinetics, even like more qualitative attributes such as strain or purity, and quality control checks usually are also within the purview of the DSC techniques. More quantitative stuff, things such as crystallinity, melting temperature, glass transitions are all well within the scope of the DSC. So, which I'll be covering some of that in the later slides. So, sorry. One of the important thing that you can might need to consider is that different materials will have different melting behaviors. So you can see right here. So from let's say a melting of ice, water at 0 degrees C, or a melting of a polymer, the high density polyethylene, or a melting of the indium metal at a higher temperature of about 157 degrees C right here. So you can see here that there are distinct way that the profile looks. So for example, for water, there's a much sharper peak right here, and the metal is also really sharp compared to something like the polymer where you have a broader signal right here. So this is very typical when it turns when we're looking at the crystallinity of your material. So the more crystalline it is, the more distinct the melting temperature or signal that you get from the DSC curves. So I mentioned before, one of the more common applications of the DSC technique when it comes with polymer is something like in the recycling industry. So for example, here, where Camacho and Carlton published at 2001 where they looked into a different mix of polymers and how they would appear in terms of their thermal profile with the DSC curves. As you can see, like a mix between the high density polyethylene and polypropylene. You can see that the 100% HDPE has this melting curve at about 130 degrees C, and the 100% polypropylene is about 165, 166. So, the in-between mixture, you can see that like both of these profiles starts being in a combination of both. And, if you know what you're looking for, DC is definitely very good at quantifying how much of the impurities. For example, if you look at polypropylene as impurity, you can quantify that based on the DSC curves. So another a way that you can see is like in a polymer blend. For example, in a certain applications, you might start blending polymers together. You can, in this particular paper, they've used ABS and polyamide or nylon. So you can see here that there's no melting temperature at the 200 degrees C with the ABS. It's a more amorphous polymer. But as you add more polyamide, you can see that there is a more distinct peak happening occurring here. This graph shows the cooling down and what happens if crystallize once you melted the blend. What are the crystallization temperature? And you can see that the different behavior occurs depending on the blend that are available. So again, there's really no crystallization with the amorphous ABS, but the different polyamide blends will start having different profiles. Another important application by DSC when it comes to like something like a PCM, where now you're looking at the phase change materials. So phase change materials are materials that readily changes phases between their solid and liquid form, depending on the conditions applied. So different temperature. You can see you can look at it as something like a wax where it melts at liquid form and then readily forms back into its solid form. And it has certain applications in energy storage applications. And DSC really plays an important role in characterizing PCMs. Is that you can characterize its ability to store heat in the form of the CP or the specific heat capacity of the material. For this specific example, they measure that at the solid state, the CP is around in this range right here. And as you heat up the material to about 150 degrees C, it transitions into the liquid form, and now the liquid stores a lot higher energy. And then, in the event that you want to use or release that energy back, you can see that this is the amount of latent heat that are stored within that material. So there's like certain considerations that you might want to look at when you're like looking into PCMs or like PCMs with fillers. Is that the profile will start changing depending on the formulation that we're looking at. So from ordered to disordered, and then making sure that the amounts or the sampling that we use for PCMs represents the bulk PCMs in general. So next bit is like looking into the effect of fillers with polymers in general. So for the most part, this is pretty much how polymers or DSC curves with filled polymers are typically behave. Is that for example here we're looking at polypropylene with multi-walled carbon nanotubes as fillers. So you can see here that for a pure polypropylene, for the first heating, you can see that the melting profile looks like this, where there's a sharper peak at about 160, 165 degrees C. And once you added different amounts of the carbon nanotubes at different sources, you can see that that particular profile starts changing when you start broadening, because like, yeah, the crystallinity characteristics of the polymer starts changing as you added the filler. But one thing that you need to that are typical for this particular studies is that as you melt it and then cool it down, the effects of the filler significantly change the crystallization temperature of this polymers. As you can see, pure polypropylene, there's a significant shift in this melting temperature. This is usually attributed for the fact that the fillers itself acts as a crystal seeds where the polymer starts creating more ordered form around those fillers. And you can see that there's a much higher shift at higher amount of fillers in general. So this is a typical trend when it comes with filled polymers and how the DSC can help you characterize its thermal behavior. So in terms of crystallinity, I've been mentioning it throughout the talk so far, but I haven't really defined what exactly it is, right? So in terms of crystallinity, there's typically three definitions in terms of with polymers, is that it could be amorphous, where it's like a random distribution of your polymer pieces within the structure itself. And there is a semi-crystalline, where now you have a semi-ordered, where you have a combination of less ordered amorphous aspect of your structure with a more ordered crystalline part of the polymer, and in an ideal world where it's going to be 100% crystalline, where you have only ordered structure, where your polymer is very highly oriented. So between amorphous to crystalline, you're going to have some randomness to highly ordered. And what it means is that typically in a DSC perspective, when we're doing certain measuring, what we encounter for the most part for polymers is that semicrystallines are the most common types in terms of it, because of the combination between the pros and the cons between amorphous and the crystalline. Purely crystalline polymers exist, but they are very rare, and typically they are more expensive side of things, very highly engineered polymers, and semicrystallines are what we typically would associate with most of the common types that we have in an everyday setting. So from a DSC standpoint, when we do measurements, amorphous types of polymers do not really show any melting or crystallization peaks. What they're associated with typically are glass transition, so softening temperatures, but they don't show any melting point. For crystalline polymers, it's the opposite, where it's very hard to really look at glass transitions, but there are very well-defined melting temperature or crystallization temperature. Semicrystalline combines both of the aspects of this two, where you have typically you'll have a little bit of a glass transition and a melting point. And DSC can offer you can measure how crystalline your polymer would be by measuring the degree of difference between your glass transitions and the melting points. So a very common amorphous polymer would be something like PMMA, and there is something along the line of like when you measure amorphous polymers, there's certain complication associated with this particular types of plastics. Is that depending on the manufacturing process, depending on how they were extruded, for example, sometimes we create what we call thermal history into your polymer, and what it means is that you get random rearrangement of your polymer, but it's not quite in a most thermally stable state yet. So, for example, here you can see that like a first DSC measurement of this particular PMMA, you can see that there is some sort of endothermic peaks occurring at about 84 and 117 degrees Celsius. But then when you take the same sample that underwent the first run and remeasure it with the same condition, you can see that that endothermic peak suddenly disappears. And now you only have this glass transitions at about 100 degrees Celsius. So sometimes when you're dealing with amorphous polymers, you have to make sure that you thermally treat it first to make sure that any chance that there is that thermal history associated in that particular product is removed, and you can go ahead and actually identify the glass transitions. The same phenomena is observed when we're looking at something like a random copper wire coated with this polymer right here. You can see the first run, there's a glass transition occurring here, but then there's that endothermic peak again, and then if you do a second run, that endothermic peak disappears. So basically what we're doing here is just like we're treating the thermal history out of the equation and actually do the characterization accordingly. Another important information we can get from the DSC technique would be something like a melting profile. So in this particular specific study would be something like a nylon. So nylon exists in different forms: nylon 6, nylon 6/6, and nylon 12. And you can see that they all have nylon is typically considered as a semi-crystalline with a more crystalline characteristics to it. But you can see here, because of there's a minor glass transition occurring between 30 to 50 degrees C, you can see that nylon in general is some amorphous aspect to it. And different nylons would melt at different temperatures. So this is very important when we're looking at processing a perspective. So you can see that something like a nylon 12, for example, is the least heat resistant of all the series that's shown right here, with nylon 6/6 being the most resistant due to the higher melting temperature. But there's also important information in regards to something like if you're going to consider like 3D printing your polymer, where you're going to need to make sure that you are using the right conditions for a very specific material. And again, we are looking at the low density versus high density polyethylenes. You can see here that the high density PE shows a more crystalline characteristics because of its sharper, more well-defined melting curve, DSC curve. And you can see there the LDPE is more, there's a lot more randomness and a broader peak in there, showing that the LDPE has less crystallinity compared to the HDPE. So both of these polymers are considered semi-crystalline. It's just the HDPE is more crystalline than LDPE. And that's, again, thanks to the DSC curves. So now we're looking at the PET, polyethylene tetraphthalate. You can see here that the crystallinity is an important factor that we need to associate with it. So you can see here that the top blue curve, this is the first run for the DSC curve, and what happens here is that we're doing a certain thermal treatment, specifically by doing different cooling rate as we go to the different stages in the test. So the first test, we heat it up all the way to about 300 degrees C, and this is the DSC profile we were able to get. So you got the glass transitions and some melting peaks right there. As we cool it down in a lower slower rate, you can see that when we actually do the test again, you can see that there is still glass transition right here, but now you have a more well-defined peak, indicating that the PET becomes more crystalline. And again, that's mostly because we gave it enough time to cool down in a slower rate, enough more of the crystalline part of the polymer to form into a more ordered fashion, and less of the amorphous factor into it. However, if we do a very quick quench, so we're not giving that crystallization to occur, we can see that it's in a more amorphous state. So you can see that the glass transition is more pronounced. There is actually a cold crystallization occurring here, and now you still have that crystallization or melting peak right here. So this indicates that thermal treatment of any polymer is also another factor that we need to account for when in terms with semicrystalline in general. And it's reversible in a sense that, like, if we start from a more amorphous state right here, this was done by having a really quick cooling rate at about 80 degrees C per minute. And then if we decrease the amount of cooling rate into a more slower rate to 20 to 10, you can see that these amorphous signals are starting to disappear with, and now you have more of a crystalline profile for your PET. And what's really cool about this PET is that, depending on something like, if you take a bottle, like a plastic bottle made of PET, different parts of the bottle will show different profile in terms of its crystallinity. Is that you can see here in the DSC curve, so for both top and the bottom, you can see again that there is a more pronounced glass transition and this cold crystallization peak right here, which indicates again an amorphous characteristics, is that the top and the bottom are both amorphous, while the sides or in the middle bit right here is more crystalline characteristics. And we're not just looking at thermoplastic polymers, so polymers that melt or at high temperature. We're also looking at thermosetting polymers, and we can study it using the DSC. So, for example, this particular specific adhesives. So, for the first run, you thermally treat it, and this particular adhesive sets based on the available temperature. So, at higher temperature, it starts setting. So you can see that there is an exothermic event right here, which is associated with the setting. You can get the energy under this curve that will be associated with your curing energy, basically. And if you repeat your test after this particular run, you can see that exothermic peak disappears, and now you're left with a glass transition, indicating that your resin or your adhesives is fully cured. So DSC is very useful in a sense too, that you can detect that on how complete your curing is on that particular condition. So with the same experiment, but with the different adhesives, you can see here that the first run shows so it's semi-cured resin. So you can see that there is a glass transition, but there is still that slight exothermic event occurring right here, which is associated with curing of, or some parts of it is still not cured. And again, you can do the second heating, and that particular peak disappears, and then indicating that your adhesive is fully cured. So again, you can use DSC as something like something to quantify or qualitatively check whether your process is complete or not. So again, at this point, I've hopefully showcased that DSC plays a really important role in terms of qualitatively and quantitatively, in terms of identifying, profiling on how the polymers and polymer composites behave under thermal treatment. And I would like to just kind of add that we can enhance that insights by having more capabilities added into your DSC. So in this particular, so we've us in C-Therm here, we're partnered with Rigaku with their DSC Vesta right here, and more specifically, its capabilities of sample observation. And what it means is that you can add a layer of understanding and completeness in terms of having a full profile of the story of how your material behave under your test condition. So we can infer a lot from how your DSC curves are looking once you've done your testing, but having a more proactive approach where you actually have another reference point of seeing how your materials behave exactly at particular temperature points is going to add it to the value overall of the experience in general. So DSC Vesta right here, you can see that we have a sample observation all the way to about 350 degrees C. Rigaku has a newer Vesta 2, which you can we can do the sample observation all the way to about 750 degrees C Celsius. There are certain add-ons we can also add into the unit where we can cool something down to all the way to minus 190 or minus 170 cryogenics, or you can have your UV lights if you're looking at curing under UV induced polymerizations, for example. So there's an add-on of a UV light in the thermal or test chamber right here. And also if you're looking for automations, there's an auto sample changer that are available with the Vesta on top of it. So again, you can see that in a sample observation, add this extra value with a DSC. So in this case, you can see that there's this is a sample right here. You start heating it up all the way to about 100 degrees Celsius. You can see that in that DC there's a thermal event occurring. You can see that is associated with the melting of the material right here. And then as we cool it down with a temperature right here, you can see that the reverse is occurring where you started having crystallization right here and a more exothermic event, which is associated with really, solidification of that liquid crystals. And again, that second event right here. So again, we can get a lot of value from looking at the DSC curves itself, and then if we have a good understanding on how exactly the material will go, we can associate this event as like, oh, this must be melting, and this must be crystallization. But having that more tangible data in terms of seeing exactly how the material is behaving under these conditions is added value overall. So again, this is just notes on exactly what the events are happening. So you have melting to liquid crystal form into liquid form, and then back to liquid crystal to really in this crystallization events overall during the heating and the cooling process. Another thermal analysis, we can use DSC in tandem with other tools in our repertoire here. So we have the TMA, thermal mechanical analysis, which looks at the expansion of your materials over temperature. So it's very useful for something like glass transitions and softening temperatures. And also, again, describing how your material expand under change of temperature. And we have here is the STA, simultaneous thermal analysis, where you can have a TG, thermogravimetric, and DSC capabilities at the same time. So change of mass as the thermal event is occurring. So one of the few examples you can hear. So for example, for the TMA, we can combine that with the analysis of the PET again. You can see here that this is the DSC curve. So we know that there is a glass transition, and then there is a crystallization event at this temperature. But we don't exactly know what happens to the physical part of the sample. And the TMA shows that here, you can see that there is a change in the TMA data at the glass transitions, but you can see here that the sample actually shrank after the softening part. And you can see here that after crystallization, it stabilizes there. So that's something like an added value again, if you're looking at polymer studies. So you can't just fully rely on a DSC with trying to understand your materials. And in terms of and again, more video right here. So again, polyethylene terephthalate. You can see here that with the STA, now you have a TG and a DTA data. So similar to DSC, You can see here that as there's a shift because of the glass transition, as you heat it, increase the temperature. There's no change in the mass, so there's really there's no destructive process occurring with your material. So that's a very good information to know. And you can see here that as you heat it some more, you can see that it's undergoing a cold crystallization, and it's going to start being opaque as it becomes more crystalline. And again, no change in the mass, but then as you heat it some more, you can see that in a sample observation right here at some point, where as it approaches 250 degrees C, it started to soften, right? You can see that the polymer is starting to expand a little bit, and as it reached that melting temperature, the plastic melts. So as we keep heating it and reaching the composition temperature, you can see that the polymer starts yellowing, and again, slowly but surely right here. And that's also due to the oxidation, right? So this test work done under air. You can see it start bubbling. You can see that now that the mass starts changing, because now you're basically reacting and consuming some of the material due to the reaction. And you can see that the data becomes erratic because now you have a loss of the sample. And in terms of the DSC or DTA data, this is pretty much nonsense, but you can see that there is a lot of information I can gather that the particular conditions. And again, this is PLA now, associated with plastic straw, but this time it's DSC, ST, and TMA. You can see that in the TMA condition here, there's different softening parts with associated glass transitions, melting, and another melting. And you can see that there is no decomposition happening because there's barely any change in the TG material. And again, more of that DSC/DTA, where you can see that in this biopolymer, as you increase the temperature, you can start associating like softening of your material here, and then at reaching this particular temperature, you can see that there's a massive oxidation event, big, and you can associate that with the darkening of your material. And again, hopefully I've went over the importance of understanding how exactly we can convey or use the DSC technique and other associated thermal analysis techniques, such as the STA and the TMA, in order to really well characterize the material. So in this case, this is again polyethylene terephthalate, and really have that a bigger picture on how we can understand the behavior and how we can adjust the processes and the methodology or methods around the data that we get from these studies. So with that, I think this is the end of my webinar, and I'll just give it back to Arya here for questioning.
All right. Thank you very much for that, Genesis. Yeah, folks, so just to close out today's session, a little bit of an outro here, and then we'll spend a few minutes to go over the Q&A. So for those, found this interesting, or if you would like to maybe dive a little deeper on your own, we do have a variety of webinars as well as technical publications available on our website. So, again, looking for similar topics or, other related to either the DSC, thermal conductivity, or MetroVib, definitely feel free to take a look there. There's plenty of resources available for you to take advantage of. If you're not already doing so, give us a follow on LinkedIn. If you want to keep up to date with latest, upcoming webinars, blog posts, different events, technical pieces, this is where we put it first. So if you want to keep up to date with us on that, just give us a follow, and we'll be sure to keep you informed. Wanted to mention some upcoming webinars. So for those who are interested, coming up October 22nd, we'll have a dive onto dynamic mechanical analysis theory and applications, again, focusing on the Metrovid product line. Little bit, let's see, oh yeah, November 12th, we'll be doing a thermal conductivity measurements theory and applications, focusing on the C-Therm product line. And then November 19th, doing more of a TMA theory and applications focus, again, with the Rigaku options. As far as events, for those who might be in the area and are available to stop by, love to have a chat with you kind of in person, one-on-one. We will be at the International Thermal Conductivity Conference held in Charlottesville, October 27th to 30th. We will have a booth there, the booth number to be determined. And then later in November, we'll be at the Polymer Testing World Expo North America. That's November 13th to 14th in Cleveland, booth T1535. All right, so that brings us to the end of the formalized session here today. I'm going to go ahead and stop sharing. At this point, we're going to go into a little bit of a Q&A. So for those who need to drop off at this point, just like to say thank you very much for joining. We'll end the formal recording here, but looking forward to seeing you guys at the next one.